Welcome to the presentation on the problem. Remove all occurrences of a substring. In this session, we will walk through the problem statement, approach, and solution in C++. In this problem, we are given two strings S and part. Our task is to remove all occurrences of the substring part from S. After performing the removal, we need to return the modified string. The goal is to continuously remove the substring part from S until no more occurrences are found. Here's how we can break it down. First, locate the first occurrence of part in S. Then remove that occurrence from S. Repeat the process until part is no longer present in S. To solve this, we make use of two main functions in C++. std::string::find is used to search for the first occurrence of the substring part in the string S. std::string::erase allows us to remove a substring from S, starting from the position where it was found. Let's walk through the algorithm step by step. Use find to locate the first occurrence of part in S. If found, use erase to remove it from S. Continue this process until part is no longer found in S. Finally, return the modified string. Here's the C++ code that implements the solution. We define a function remove occurrences that takes in the string S and part. Inside the function, we repeatedly search for part in S and remove it. The process continues until no more occurrences of part are found. In the main function, we test the code with an example where S equals to TAAB, CB, AA, B, CB, and part equals to ABC. And the output is DAB after removing all occurrences of ABC. Now let's go through the code. In the main function, we defined S equals to TAABCBAABCBC and part as ABC. When we call remove occurrences, the function will find and remove every occurrence of ABC. The result after all occurrences are removed is DAB, which is printed as output. The key functions at play here are find and erase. Let's talk about time complexity. The find function operates in big O of n time, where n is the length of the string S. The erase function operates in big O of m time, where m is the length of the string part. In worst case, the overall complexity is n times m, depending on how many times we remove part from S. Let's consider some edge cases. If S is empty, the result will simply be an empty string. If part is not found in S, the string remains unchanged. If part is longer than S, we can't find it, and S stays unchanged. In conclusion, this problem can be efficiently solved by repeatedly finding and removing substrings. By using find to locate part and erase to remove it, we get a clear and concise solution. This approach can be applied to many similar string manipulation problems. Welcome to this presentation on checking for binary search trees or BSTs. In this session, we will explore What makes a tree a BST? Analyze some examples and implement a solution in C++. The problem statement is simple. Given the root of a binary tree, we need to determine whether it is a binary search tree. A binary search tree is a tree where every node follows a strict ordering rule. The left subtree contains nodes with values less than the current node, and the right subtree contains nodes with values greater than the current node. We also assume that BSTs do not contain duplicate nodes. The constraints are as follows. The number of nodes ranges from 1 to 1 lakh, and each node's value lie between 1 and 1 billion. A binary search tree must satisfy three conditions. First, every node's left subtree should contain values smaller than the node itself. Second, every node's right subtree should contain values greater than the node. And finally, both left and right subtrees must also be BSTs. This ensures that the entire tree maintains the BST property. Let's take an example. Consider a tree with nodes arranged as follows. The root is 2 with 1 as its left child and 3 as its right child. Additionally, 5 is the right child of 3. Since all nodes satisfy the BST conditions, the output is true, indicating that this is a valid BST. Now let's look at an invalid case. Here the root is 10 with 5 as its left child and 20 as its right child. However, in the right subtree there is a node with value 9 which violates the BST property since it is smaller than 10 but appears in the right subtree. Therefore, the output is false, meaning this is not a valid BST. How do we verify whether a given tree is a BST? The approach is simple. We use a helper function with minimum and maximum constraints. If the tree is empty, it is considered a BST. Next, we check whether the current node's value lies within the permissible range. Then we recursively validate the left and right subtrees, updating the constraints accordingly. If all conditions are met, the tree is a BST. Now let's implement this logic in C++. We define a helper function isBST that takes the root node along with minimum and maximum constraints. If the node is null, we return true. Otherwise, we check whether the node's value falls within the valid range. If not, we return false. The function then recursively calls itself for the left and right subtrees, updating the constraints accordingly. Finally, we call this helper function from our main isBST function, setting the initial constraints to negative and positive infinity. Let's analyze the efficiency of our approach. The time complexity is big of n since we visit each node exactly once. The space complexity depends on the recursive depth, which is big of h, where h is the height of the tree. In the worst case, for a skewed tree, this can be of big of n, while in a balanced tree it is big O of log n. To summarize, we have learned that a BST follows a rule where left nodes are smaller and right nodes are larger. We implemented a recursive solution using min-max constraints to verify a BST. The solution runs in linear time and efficiently checks for a BST validity. We also covered multiple examples to solidify our understanding. Thank you for your time. I hope this session helped you understand how to check if binary tree is a BST. If you have any questions, feel free to ask.